So if you're a pattern person, and if you're somebody that recognizes patterns, and then this is easier for you, okay? Have you guys known all along, with all the functions we've been doing, they have been patterns. So functions are patterns. They're a pattern and a rule that you follow. So we are going to use, sequence. I'm going to get used to using a sub n. I don't know why, I didn't have a chance to edit this. I meant to edit this. S is going to stand for sum. So I'm going to use a sub n or b sub n or c sub n as our sequence notation. So if you guys would switch that s to an a or a b or whatever. So a sequence is a function whose domain, the domain is specifically positive integers, but the range will follow a pattern. And that's what a sequence is. So it's a little different because normally with with functions, we can go in the negative direction and whatever, but we're treating this 1, 2, 3, 4, 5 as term number 1, term number 2, term number 3, and so forth. And so we use a little subscript to note what the nth term is, okay? So if a formula follows a sequence rule, we call this formula the nth term formula for it. Okay, which is just general. We're used to seeing as y equals, and we're going to call it sequence. We're going to put it in sequence notation. Okay, if we go all the way up to like ... n, then the rule will always go right there. Sequences are nice. If we give this to you this way, this is essentially just an explicit formula where we're going to do a recursive definition as well. But this is called an explicit formula for a sequence. And on these ones, you could directly plug in. That's what's nice about these ones. So for instance, if I want to know what my first term is, and I want to find a sub 1, I get to plug 1 into my n. Oh my gosh, my brain isn't able to talk n right. I get to plug in a 1 into my spot where my n is. Pretty easy, pretty straightforward. So 2 minus 1 would have been a 1. So let's find our second term. 2 times 2 minus 1 puts us at, what is that, 3? Let's go to our third term. 2 times 3 minus 1 is 5. Fourth term. 2 times 4 minus 1 is 7. Fifth term. 2 times 5 minus 1 is 9. ... Okay? What are you noticing about the numbers in the sequence? So the sequence is the range, your y direction. Your y.
They're all 2 greater.
They're all 2. What does that relate to when you are noticing the equation up there?
This is times by 2.
Yeah, this one looks like it's a 2n. So are you noticing that when I was adding 2 every time, it related to the what? What kind of a function does this look like? This is going to apply to less than 28. What does this function look like? It starts with an L. It's linear. So if it looks like I'm adding it 2 every time, notice that relationship, which we'll circle back to that. This is just general making some kind of inferences. All right, we're going to call each of those a term. This one didn't really copy very well. That's supposed to be a sub n right here. And then 3n squared plus 1. Same thing. If I just give you an explicit formula, are you okay to plug it in? Perfect. If I ask you to find the first few terms, hopefully you guys would be okay to plug that in and follow the order of operations. So on this one for your guys' terms, what's a higher priority, the timesing or the exponent? The exponent, and then you times, and then you guys add. Everybody okay if I skip that one just a little bit? The explicit formulas are super straightforward. All right, so part of your homework, is, like I said, is just kind of getting your bearings with sequences and understanding the notation. So like I said, we might use B once in a while, and if I just straight up give you a sequence and you just literally plug in the first few terms. You can organize them as a chart like I did. You can also just kind of organize them however you guys want. So B sub 1, and I just simply plug it in. Take care of the top first, and then see if things cancel from top to bottom, and if they don't, you're good to go. Okay? Now, this one is going to be a little bit harder. It gets harder and harder to pick out the type of sequence it is, and so that's why this first lesson is just general, and then you're going to have specific sequences for 13 or lesson 27 or 28 and 29. Okay? But I think we're all getting the gist that we're just taking them and plugging them in when they're given to you in this form. Who remembers this from last year in your guys' courses? It was the last lesson taught in regular math 3. I don't know about honors, but close to your last lesson. Remember it? Mm-hmm. Awesome. Pretty much everything you learn these last 4 lessons are exactly from math 3. So you probably won't be shocked with anything that you see. All right, I just wanted one good full answer for your notes, and then I might not do some of the other stuff. Let's see, is this 11 over 10? Yeah. Awesome. Now, when you guys are trying to pick out a formula, hopefully you can step backwards and you could recognize patterns. And sometimes it's hard to recognize patterns when they're in fractions, but sometimes you can look like the numerators and be like, oh, my numerators are all jumping up by 2. Oh, my denominators are all... they're all just 1 lower than the number that they're. Does that make sense to everybody? Kind of a little bit. You can kind of separate it when you're trying to come up with, some rules. Some examples of some sequences are right here, and I don't want to take the time to go through and try to come up with the rules just because we have so much to accomplish. But as you guys get good at your number sense, you can start trying to recognize what's happening. Do you guys recognize what's happening on this one? The second one. I always start by adding and subtracting, then I go to multiply and divide, and then I go from there. What did you guys notice about this one? Not really a nice one, is it? Oh, okay, well. Oh, okay. Oh, but then it's back to being, you know what I mean? So sometimes some patterns are a little bit tricky. But I'm going to go ahead and move on because we're not going to pick out a rule on those ones because it's too tricky to pick out a rule without a good formula, and we'll learn that formula tomorrow. Okay. I want you guys to be capable of picking out a rule when we give you nicer stuff. Those ones were really, really random and crazy sequences, and this one is a little bit easier to pick out. Okay? Can anybody pick out what you guys would pick for your nth term? And one way you can organize it is try to take n and then call this a sub n and be like, I'm at term 1, I'm at term 2, I'm at term 3. And you're like trying to pick out the rule. And then when you guys get to n, you guys are going to write your rule right here. Or you can come over here and just write your nth term over here when you're done. Okay? So a couple of hints when you guys are trying to figure out your different rules. I first start by... Here's my hints, my step-by-step my brain goes through. I first start with the easy stuff. Am I adding or subtracting? And it's the easiest to check out. Then I start seeing if I am timesing or dividing. Sometimes you have to check for like the second layer, like the second step, like I was adding by a 1 or 1, 2, gosh. I was adding a 1, then I added a 2, then I added a 3, and then the second layer is saying, oh, I'm changing by a 1 every single time. So sometimes you look at the second layer. The other thing you can look at and you can do is sometimes separate the numerator from the denominator and come up with the rule of the numerator and the rule of the denominator. And so these are all just little strategies to come up with, okay? So I want to look at this one and see if we can figure it out. And you want to see how you can rewrite it in terms of n so that it is how it works based on whatever term I'm at. So this one's a little tricky to pick from here. So when I look at this, does anybody have an idea based on this being the second term by chance?
Divide by 3.
Okay. Another way to view that is what? Timesing by a what? 1 over 3. Okay, let's see if that sticks. Times by a 1 over 3. Timesing by a 1 over 3. So let's write that as a rule. Let's just try this. Timesing by a 1 over 3. And let's put in, when I'm timesing, where would I have to put n when it's timesing? It's not 1/3 times n, because if I'm at my first term and I plug in a 1, that would have to be a 1/3. And if I'm at my second term, that'd have to be a 2/3. So it's not 1 times n. Let's try this one. What about 1/3 raised to n? That still kind of doesn't work. So, what did you just say?
N over 3.
Let's try that. If it was n over 3, that would be a 2/3. This would be a 3/3, but that's a good shot. Okay, any ideas based on maybe this being a 2, like this is a 3 to the first power, this is a 3 to the second power, yet I'm at the third term. This is a 3 to the third power, but I'm at the fourth term. Yeah, n minus 1. Good. Did you say n minus 1?
Yeah.
Yeah. So if I'm at this term, let's see if that works to plug in a 1. 1/3 to the 1 minus 1 is a 0. Is that a 1? Yes. Let's plug in a 2. 1/3 to the 2 minus 1, and then we came up with the rule. Okay, so sometimes if based on what term you're at, you got to use n minus 1s. Another way this could have been written is a 1 over 3 to the n minus 1, and then just view the numerator as staying a 1 the whole time. So that could have been another way you could have viewed the rule. All right, how many of you remember what a factorial is? 3 factorial, 5 factorial, 10 factorial, 0 factorial? What's that?
Like 1 times 2 times 3.
Yep, you go all the way down from that high number. So you take n times n minus 1 times n minus 2, and you go all the way down to 3 times 2 times 1, okay? You guys do have a calculator or a button in your calculator. So those of you who don't want to always write it out, I think it's sometimes longer to find the button in your calculator than it is just to do the math sometimes. So sometimes I just do the math and sometimes I find the button in my calculator. Those of you who have the typical TI-30s, it's the probability button. PRB is the probability button. It's the second one over, second one down. PRB. Those of you who do not have the TI-30s, you guys have maybe this is a 30. Those of you who have a Casio, I probably have to help you find it or Google it really quick. Those of you who use your graphing, you need to be able to use it. The other one's on the test. But those of you who have the graphing ones, this is a Casio one.
Which one do you click on first?
Oh, it is one. So if I go to, the Casio graphing one. Yours would be under, you might have to look up where you can find it. I think there is. You can find them online. Yep. If you can have trainings, there are trainings for special calculators, which are awesome. Okay. Did anybody not find the factorial button? All right. So let's find 5 factorial in your calculator, or you guys can take the time to times it out. What did you get? 120. Did anybody find 10 factorial in their calculator?
3628800.
Big number. Okay, what about 0 factorial? It's actually 1. I know that's weird. There's a proof on it in one of my classes, but we don't have time to talk about it, and I don't remember the proof exactly, so just kind of go with the flow on that. 0 and 1 factorial are 1. So 1 factorial is 1, and 0 factorial is also 1. Okay? Now, don't waste time. I would not waste time putting something like this in my calculator all the time. Sometimes it is. You're going to be doing a formula for this when we get to binomial theorems. You're going to be doing this formula. And I think it's too time consuming to maybe necessarily put it in. Plus you guys will forget to sometimes put parentheses. So is there another way that you guys can use factorials efficiently?
What is the answer not 346? For the 8?
Do the 8.
For 8?
Let's try to talk about this really fast. Yeah, I don't know, what did you calculate it out to be?
Can you just 336?
Yeah, it is. So really quick, you guys can put this in your calculator, but I also want to teach you something else. There is a 5 factorial in 8 factorial. So like 8 times 7 times 6 times 5 factorial. Are you guys with me on that? there is always this number in the bigger numbers somewhere, right? And so from 5 factorial down, they can cancel. And so they can 7 times 6. So those of us who sometimes want to simplify and not have to just always put stuff straight into the calculator, there are strategies to be efficient there. Here's an example. What can cancel with the top and bottom? 82 factorial can cancel, right? Oops. Ugh. 82 factorial gets to cancel, okay? And then I still have this 5 factorial, so maybe it's not going to save you time, but all I'm saying is you can cancel factorials all down if you need to. Looks like I could pull a 5 out of this 85. What's left on that one? I heard it. What? 17? 17? So,
It's 5 divided by 8.
yes, thank you. How many times can 4 go into 84? 21? So you can still do stuff without having your calculator or having your, does a 2 divide in anywhere?
Wait, why did 3 cancel out?
Did it cancel out?
You just have a marker there.
What canceled out?
3.
Oh, I was about to cancel a 3. And then I realized it didn't. Oh no, I did in the 21. I canceled the 3 to the 21.
Oh, okay.
Okay, so you can say 17,783 over 2. But all I'm saying is you don't have to use the factorial if you guys don't want to. But the button is there. But this is how you would do it without that button to make it more efficient. Does that make sense to everybody? Okay, so you can cancel factorials down if you need to. All right, we're using this formula later. It can be part of some of these sequences, so that's why we taught it now, but we're really going to be learning using it more in lesson 30. So just kind of table that until we get to lesson 30. Okay, there's another way to see sequences. There's a recursive definition. Recursive definitions don't work like explicit ones. I cannot use a recursive definition and quickly say, so those explicit ones, I could ask you guys to find term 100. And you could take 100 and plug it directly in. Recursives don't work that way. I can't jump clear up to 100 and find that term. So a recursive sequence is one where you have to use previous terms. So without the previous term, you're usually unable to be able to use this definition. So suppose we have 3 terms. So suppose n is 3, and if I am going to be at my 3rd term, and I do a sub n minus 1, n minus 1 stands for the term prior. So if I'm at my 3rd term, a sub 3 minus 1 is my 2nd term. So my 2nd term is the previous for my 3rd term, okay? So it just simply means previous term. Anytime you guys see an n minus 1, just think previous term. If I see n minus 2, that means I need how many previous terms? The one that's 2 away. Does that make sense? So if I'm at n minus 1 is this one, n minus 2 is 2 previous terms, n minus 3 would be 3 previous terms. So are we okay using that subscript n minus for the most part? So that's just a recursive definition. So here's an example of how to read this definition. Putting this in our own words is saying take 3 times your previous term and then minus a 2. Okay? So in order to find my first term is 2. So in order to find my 2nd term, I do what? I plug in 2 to the previous term spot. What is that, 4? So to find my 3rd term, I take 3 times what? 4, and then minus a 2. So to find my 4th term, I would take 3 times my previous, and then a minus 2. What did you guys get? 28? Am I doing that right? And then my 5th term, I would need 3 times my previous, and then a minus 2. 3 times my previous puts me at 82, right? Okay. Do you guys feel okay about a recursive definition and seeing it in a different way? Alright, there's explicit and there's recursive. Okay, Zach.
So, on the first one, or the second term, 3, 2 to the 0, which is 1. Like, would you do that again?
Do this one again.
The second one.
So 3 times my previous term. So since I'm at my second term, I do 3 times, and then when I put a 2 minus 1 here, it's times the first term.
Oh,
So that's what the n minus 1 means, if you were to plug it into the n. But we don't take the time to plug it in the n. We essentially are just hoping you guys realize that stands for previous. But you're more than welcome to have called this a sub 1. And you're more than welcome to call this a sub 2 and a sub 3 and so forth. Good. Okay, way to clarify. Anything else? Let's do one more recursive look. I may not do all 5 just so we can move on, but let's do one more recursive. So would you guys put in your own words, oh, this is supposed to say A, or those are supposed to say C, but I'm going to say A. Okay. Sorry about that C typo. That's a typo. Can anybody put in your own words what this recursive definition is saying? Take 2 times the previous and add a 4. And they want you to find the fourth term. So I have to know the second term. 2 times my previous plus a 4. What's my previous? -3. Good. Good. To find my third term, 2 times my previous, add a 4. Did you guys get a 0? So they want your a sub 4 term, so 2 times my previous and then plus a 4. Did you guys get a 4? Awesome. Okay. All right, recursively, I hope you guys feel pretty good. This lesson, like I said, was just introducing patterns, introducing notation, introducing recursive notation, and it's like a notation lesson until we get to the actual rules, okay? We'll actually memorizing formulas. So let me teach you the next part for notation. Summation notation is going to be used for sequences when we learn how to find sums. And we're going to be learning arithmetic sequences in series. Series are when you find the sum of a sequence, okay? So let's just go ahead and make sure we know what this notation means. So does anybody recognize that symbol? What is that symbol? It does stand for sum. You guys usually see it in Excel sheets when they want to do sum. It's like one of your guys is like, it's one of your language, some of your words in your guys' language. Sigma? It is sigma. Oh yeah. Someone talk in your language for a second. Give me a statement.
I'm so glad
No one's so sigma.
No, I know. Give me like a long sentence though. Or do you guys not talk like your species? I kind of feel like your age of kids is like a different species.
When doing
Would you talk in your language for me?
so sigma.
Just kidding. I heard Sigma's out, actually. My 5th period is like, ew. It's so out. I was like, oh, is it? Everything's out within months of 2 days. Okay, I'm kidding. But it is called sigma. Okay. So sigma stands for sum. It's a Greek symbol. This is called sigma. And I want you guys, the way we use sigma, I think sometimes some of the stuff goes that way. And some programs, you're going to notice, because I had to reformat, because a lot of things were just really wonky when I reformatted them here. You're going to notice sometimes it's popped out front here. So I don't have a lot of space. But we're going to have a k equals 1. We're usually going to put n there. And then your rule is going to go here. We use a k when it's in sigma notation because we go to the nth term. Okay? So this is the nth term. Or the rule that your equation follows. Okay? So if I were to say this in a sentence in math language, this whole symbol tells me a whole sentence. It's kind of cool because there's a lot of symbols in math, and I can give you like a line of symbols, and it would read a whole paragraph. So let me kind of tell you how you read this. Does anybody remember how to read this from last year and what this stands for?
Dylan said he'll give it a shot.
Dylan did. Thank you. Oh, dang it. That's okay. All right. I lost my voice. This as a sentence is find the sum of the sequence A sub whatever from, well, form. Oh, where's my eraser? From term 1 to term n. That sentence is that little symbol right there. So whenever you guys see a sigma, you guys are going to look at it and you're going to be like, oh, we are finding the sum from, and I don't have to start at first term. I could start at fifth term. If this had a 5 here, it would mean I'm doing k equals 5 to 12. And I could be adding term 5 to 12. So n keeps it generalized, and then as soon as there's a number there, then you can actually find an actual sum. Okay? Who remembers this notation from last year now that we kind of like put that sentence on the board? Kind of? Okay. It's the very last lesson of the year, and you know how you guys are at the end of the year. Sometimes we're like checked out, we're burnt out, and so it's kind of hard to learn it. Okay, let's hurry and go through a couple of these notations. Let's go ahead and pick out another term and express stuff in sigma notation, and that's it. And I'll let you guys take a break before we talk about arithmetic, okay? All right. Would you guys evaluate A and tell me what we're asking you to do? Evaluate A. Just substitute what? Start at 2. Good. I want to go from term 2 to term 5. So I would plug in a 2, and then add that with plugging in a 3, and then I plug in a what? 4, and then I stop when I plug in a 5. That's what this is telling you to do. That's you writing out its sum. But because we did end at an actual 5 versus ending at an n, we get an actual number in the end with this one. Okay? So we are going to just calculate it out, and someone can help me. 4 plus 9 plus 16 plus 25. If anybody kind of started doing that for quick math, that would be awesome. I think I have it. Is it 54? Good. Good. What's this one asking us to do? 1 to 3, right? So we're going to find our first term by doing 2 times 1 squared plus 1. Our second term, 2 times 2. Because there's more calculation, I'm kind of separating these into their own piece of like work here. But I took the time to do that formula. That's the formula or the sequence. And then I replace 1, 2, 3 into it, right? So it ends up being a 3, 9. Is it 19?
Yep.
Good. So 3 plus 9 plus 19. What'd you guys get?
31.
Say that one, okay? 31. Perfect. Okay. They might have a factorial, and it's the same thing, just making sure. Ooh, that one formatted weird, sorry. So here's your factorial. Then it's the same thing as saying 3 factorial, 4 factorial, 5 factorial, stopping at what? 6 factorial. And then I'd have you guys put those into your calculator. I would press enter after, or no, you could probably put it in straight as 3 factorial plus 4 factorial. I bet you could just enter it as. Do you guys want to practice and let's see if you can do it? Make sure you could put in any of these different formulas. What did you get? Did you get it?
870.
870. Perfect. Okay. If it does stop at n, what this means is it's just writing out the sum. And the way you would probably show this is just 1 over 1, 1 over 2, and do at least 3 or 4. And then you guys are allowed just to be like dot, dot, dot until whatever. And your rule is technically this rule. Does that make sense? So if your rule is 1 over k, that's the rule that you would end right here. And you can't really find a sum when we leave it generic with an n. Cool?
So there's not an answer, it's just a sequence.
This is just the listed out sequence. That's the series. When they say write out the series or the sum, so you just write out. All right. This one was a slight typo, but not a lot. It's just a little typo. My formatting was weird, so I had to just erase it. But this was doing k equals 1. But this one, I can see them doing a weird theory type question on true or false. Is there anything to plug 1, 2, 3, 4, anything to plug into? No. So what's the sequence? 4 plus 4 plus 4 plus term 1, 2, 3, 4. So that's enough. Does that make sense to everybody? So don't overthink it when you're like, but there's nothing to plug into. That's okay. It's still 4. Everybody okay with sigma notation? All right, let's go backwards and put these expressed. I got a hint on this one right here for you guys. But will you guys take a moment and do this first one? Will you write it in sigma notation, how you would write that sequence out? And my hint to you is the rule is usually shows here sometimes. Sometimes it doesn't, but sometimes it does. And I want you guys to base things based off of what term you're at. So whatever n is, see if there's a relationship, like term 1, term 2, term 3, whatever. Is there a relationship when you come up with your nth term? So take a moment and try A. And then we'll talk about B in just a second. Okay, did you guys come up with it? This one's easy. How'd you guys do it? Did you see a correlation to whatever term you're at? Where is n on this one? N was being squared, so this was n squared. So we write k squared, starting at what term and ending at what term? And ending at 9. Perfect.
Will you put a K on the side?
We use K in sigma notation. Because we end at n, and that way you plug n into the function, you don't want to have an n and then ending at n. So we use K when it's in sigma notation.
So when count we did end.
Maybe in this specific scenario, because you're not working with n's, we probably give it to you. To use that.
So wait, can you say why do we use K again?
So because when we sometimes leave it generic and we start at the first term and go to the nth term, we need this to be in terms of something else because you're substituting n into it, if that makes sense.
So why do they sometimes use n? Like on
That's when it's not in
Example A.
sigma notation. So this is my n. This is technically called my nth term. Does that make sense?
Yeah.
And this is an nth term also. And so sometimes we give you guys sequences this way, sometimes we give them to you this way, and sometimes we give them to you as a list. And when it's in sigma notation, because we sometimes go to n, we use k's for this portion of the formula, I guess. It's just a notation thing. All right, I have a hint to you guys. Do you guys notice how this one alternates signs? Does anybody remember the strategy to come up with your nth term when your signs alternate like that? It is. You've got to somehow times by negative. So we pick the easiest number 1, okay? -1 is the easiest thing to times by, and you sometimes raise it to n, or n minus 1, or n plus 1, depending on if your first term started negative or if your second term was the negative, okay? So that's your strategy, is you guys sometimes have a little -1 raised to something when you come up with your formula. Okay, so let's try this one. Let's see if we can come up with the rule. Starting at a first term, and then this one went 1, 2, 3, 4, 5, 6 terms. Can we come up with our a sub n, like our rule that we can put into our sigma notation? I'm going to erase this. So let's think about what's happening. Okay, can anybody think what's happening to go from one thing to the next and how it relates to this being a 1 and this being a 2 technically? This first term is a 1, and then I could view this as doing what? Do you guys recognize these are what?
Square root.
They're not squares. They're all cubes. And if I break them down, this is technically 2 cubed. This is technically 3 cubed. This is technically 4 cubed, and this is technically 5 cubed. Hey, does anybody notice what's happening based on what n is and what their term is? By the way, us suffering through this helps you guys appreciate the formula we're going to be giving you on the next lesson.
So can we not remember this one?
Not this one. It's actually a different sequence than the one we're going to be doing. Any ideas? Based on what term you're at? Do you guys notice how I'm at my first term, so I can view that as a cube? I'm at my second term, I'm at my third term, I'm at my fourth term. So it looks like this is an n what? Oh, no, I shouldn't say n when it's in that notation, but k. But this is a k cubed. But that doesn't work. When I plug in a 1 cubed is not negative. I do have to have a negative somewhere. I'm going to times by a -1 either to the front or the end. Would I raise it to whatever term I'm at? Would I call this k or n? So you guys kind of base this based off of, I need this to be odd when it's negative, and I need this to be even when it needs to be positive. So my first term would be raised to a 1, right? And that would keep it negative. Did my first term need to stay negative? Yes. So I'm okay to raise it to what? Just an n or a k. I wrote n on accident in my notes, but it's a k. Do you guys feel okay about that process and reasoning through it a little bit? Okay? You're going to appreciate having a formula this next lesson. Let's go ahead and take a break for those who want to. And